Welcome to this explainer on what I like to call the impossible paradox. We've all probably stood on a dock at some point, looked out at one of those colossal container ships, and thought, how on earth does that not just plunge straight to the bottom of the ocean? I mean, we're talking about hundreds of thousands of tons of solid steel here. Sure, we all kind of know the basic physics, but seeing it play out at that massive scale, it never stops being wild. Today, we're going to look past the obvious and really decode the sheer engineering brilliance behind displacement and average density.
Just look at the contrast we're dealing with here. On one hand, you have a tiny, super lightweight metal coin, right? Toss it in the water and boom, it sinks instantly. But then on the exact same water, you have a giant steel ship packed with thousands of tons of cargo, massive engines, gallons upon gallons of fuel, just sitting perfectly peacefully on the surface. It's this crazy visual paradox that's playing out all over the globe every single day.
So how exactly does the absolute Leviathan float while our pocket change just sinks to the bottom? We're all taught that basic rule growing up. Heavy things sink. But clearly, scratch that, obviously, that rule is fundamentally flawed. Think about it. If weight was the only factor that mattered, that colossal ship would literally be an artificial reef right now. The real answer? Well, it lies in the invisible physics happening just beneath the surface. To understand this, let's take our eyes off the massive ship for a second and look right down at the waterline, right there, where the steel actually hits the ocean. The ship is physically forcing water out of its way, pushing it aside. But here's the kicker. The water doesn't just passively step aside and say, go right ahead. No way. It's aggressively pushing back, exerting this massive upward force directly against the hull.
This brings us to Archimedes' principle. We probably all remember this from science class, right? It's basically the mathematical magic that makes the whole shebang possible. The rule is that the upward buoyant force on an object is exactly equal to the weight of the fluid that the object displaces. It's this incredibly perfect exchange. To put that into perspective, if a massive ship pushes 100,000 tons of water out of the way, the ocean pushes right back up with exactly 100,000 tons of force.
All right, let's jump back to our seemingly innocent little coin. As you can plainly see, being small and lightweight doesn't automatically mean you get to float. In fact, for the coin, that compact size is its absolute downfall. It hits the water and, honestly, it essentially gives up without a fight. So why can't it displace enough water to save itself? Well, it all comes down to one crucial thing, and that is average density. See, the coin is solid metal, which means its density is significantly higher than the water surrounding it. And because it's so incredibly small and compact, the maximum volume of water it can possibly push aside is just minuscule. The math simply doesn't work in its favor. Its physical weight heavily outweighs that tiny upward buoyant force, and so it plummets. Okay, so if being lightweight isn't the big secret, what is? Drumroll, please. The true secret to floating is geometry. We're talking specifically about shape, enclosed volume, and displacement. It's wild to think about, but you could take the exact same tonnage of heavy steel, and depending entirely on how you shape it, that steel will either drop like a stone or float like a feather. Think of a giant cargo ship as basically a massive steel-wrapped bubble. I mean, if the hull were a solid block of steel, it would be chilling on the ocean floor immediately. But instead, it's meticulously engineered to enclose a massive hollow volume that's filled mostly with air. When you actually calculate the average density of the entire vessel, taking into account the heavy steel, all the cargo, and that massive pocket of incredibly light air, the overall density drops well below the density of the ocean. The air is literally what saves the steel.
It's like a constant, invisible tug of war happening right in front of us. On one side, gravity is relentlessly pulling the massive weight of the ship downward, forcing the hull to push water out of the way. And in response, that displaced water is pushing back up with incredible buoyancy. When the ship is floating steadily out there, it has reached a perfect, delicate equilibrium. That invisible balance of forces, that is the only thing supporting the entire vessel.
But, ships are working machines, they aren't static museum pieces. So what happens when cranes start dropping thousands of tons of new cargo into the hold? Well, gravity pulls harder, and the ship is forced to settle a bit deeper into the ocean. But here is the absolute genius of the hull's geometry. By sinking just a little bit deeper, it pushes even more water out of the way. This generates the exact amount of extra buoyant force needed to counteract that new cargo weight. It literally self-corrects to find a brand new safe balance.
Ultimately, the rule of averages is what dictates buoyancy. The coin's average density is strictly higher than water, so unfortunately for the coin, it sinks. But the steel ship's massive enclosed volume of air keeps its average density lower than water, so it floats. It definitively proves that floating is never just a simple battle of heavy versus light. It is entirely, 100%, a battle of average density.
However, as amazing as it is, that genius system is also incredibly fragile. The exact same physics that allow a ship to float will absolutely ruthlessly pull it under if the math suddenly changes. Ships have strict, mathematically calculated stability limits for a reason. If a vessel is overloaded, or say a breach allows water to rush in and replace that vital enclosed air, that delicate equilibrium shatters instantly. The average density skyrockets, buoyancy is completely overcome, and that safe flotation, well, it's destroyed.
We've seen the invisible, perfectly calculated balance that manages to keep thousands of tons of solid steel gracefully afloat. But remember, that balance strictly assumes the rules of physics are being respected. So the next time you see one of those giant ships gliding into port, you kind of have to wonder, what exactly happens in those catastrophic moments when human error or negligence pushes those invisible mathematical limits just one step too far?